Let's take a minute to talk about the difference between mass and weight. They are similar things, but they are not exactly the same thing. Mass is a property or characteristic of an object that does not depend on any outside factors. It's usually measured in things like kilograms. Here's me on Earth, mass of 100 kilograms. Weight is a force. It's the force of gravity pulling down on an object. And that weight, because it is a force, is measured in newtons. And because it is a force, like any other force, it is equal to a mass times an acceleration. Only in the case of weight, the acceleration is something very specific here on the surface of the Earth. It's 9.81 meters per second squared, the acceleration due to gravity that we've seen before. So to calculate an object's weight on the surface of the Earth, you simply take its mass and multiply that by the acceleration due to gravity. So in this case, my 100 kilograms of mass corresponds to 981 newtons of weight. Now, if I were to take a trip from the Earth over to the Moon, my mass would remain unchanged because my mass does not depend on outside factors like weight does. So on the Moon, I still have a mass of 100 kilograms. My weight, however, is no longer going to be equal to 981 newtons because I no longer have the Earth pulling on me with an acceleration of 9.81 meters per second squared. In fact, on the Moon, because it's smaller, on the surface I experience about 1/6 the acceleration, and therefore 1/6 the weight that I did on the Earth. So on the Moon, you would see a weight of about 163 newtons for someone with 100 kilograms of mass. In this problem, we're asked to figure out the acceleration of an object given its weight and a net force. We'll do a quick free body diagram here because it's a good habit to be into, but it's not going to be terribly enlightening for us because we're already given enough information to solve just in the wording of the problem. We have an object that's being pushed along a surface. We don't know for sure that it's level here, but we can assume it is because that's the only type of problem we've encountered so far. So there's a normal force that's pushing up that is equal and opposite the gravitational force. Both of those forces are 55 newtons. We're told nothing about the left-right forces here except that when combined together, whatever forces we have are equal to 25 newtons of net force. So if we use Newton's second law, telling us that acceleration is net force divided by the mass, we're nearly ready to make our final calculation. The only problem is that right now we're not given a mass, we're given a weight, and so we can't just stick 55 newtons in there. It's not going to come out correctly for us. We have to convert that 55 newtons into a mass. Because weight is a force, it is equal to a mass times an acceleration. Weight is a very specific force, however, equal to the acceleration of gravity times the object's mass. So if we substitute in the variables from this problem, 55 newtons equals the object's mass times 9.81 meters per second squared. That will allow us to find the mass of this object. If we divide both sides by 9.81, we get a mass calculated at 5.6 kilograms. That value can now go into our second law calculation, and we can do our final figuring here. The acceleration is equal to the net force given to us in the problem as 25 newtons, divided by the mass we just determined as 5.6 kilograms. If you divide those two numbers out, I think you'll find the answer here is 4.5 meters per second squared of acceleration. This problem is set up a little bit differently. We're given the mass of an object and told its acceleration, and we're also given a frictional force and asked to figure out the applied force. We know the acceleration is based solely on the net force acting on the object, and since we also know its mass, we can use Newton's second law to figure out the net force acting on the object without any additional figuring. And that's the first thing I would recommend doing here. The net force is the mass of 35 kilograms times the acceleration of 2.00 meters per second squared, which works out to a net force of 70 newtons. Net force doesn't go on our free body diagram, but it's going to be helpful when figuring out the individual forces here in a moment. To complete the free body diagram, let's start with the two forces that are really just window dressing on this problem, the weight and the normal force. The object's weight is equal to its mass times its acceleration. We don't really care about the number here. It happens to work out to 343 newtons, but because it doesn't matter, I think we can just go ahead and call it Fg and F normal and just leave it at that for this problem. It's the left to right forces that we're particularly interested in. We know that there is an applied force because we're being asked to solve for it, so I'm going to put that on our diagram. And we know there's a frictional force because it's given to us in the problem. The frictional force has a value of 15 newtons, which I'll just put to the left because we're not really told which direction it has to be. And that means that whatever this applied force is here, it's going to be giving up 15 newtons of force to friction and still producing enough net force to achieve the acceleration described in the problem. So when you combine the applied force and the frictional force, you have to have 70 newtons of force left when this is done. That's the only way you can get this mass and this acceleration. So that means the applied force here has to be 15 newtons bigger than 70, which is 85 newtons of applied force. 85 minus 15 gives us 70. The net force of 70 divided by the mass of 35 gives us our acceleration of 2, and everything works out with those numbers. Let's just wrap this one up with a little bit of advice on how to solve some of these problems. If you're given enough information in the problem to solve acceleration, net force, or mass using Newton's second law, do that immediately. You'll almost certainly need that third variable to solve something along the way. If you can't because you're only given one of the three variables, use a free body diagram to try to solve for net force to see if that will get you one of the answers that you need for the problem. And don't forget, mass and weight are different. It's not just about converting between the two. It's about recognizing that Newton's second law requires mass for a calculation, but a free body diagram requires weight because forces go on free body diagrams. So you should never put an object's mass on a free body diagram, and you should never put its weight into Newton's second law as the mass. Those key differences will help you avoid common mistakes as you solve problems in this unit.